our understanding of VO2 max, as we say, is not that new. If you think about it, we really date back to the 1920s. But actually, if we look at this schematic here, which was published in a tremendous book, which is the Textbook of Work Physiology by Astran and Rodell. Now, this is from their book in the 70s, but even the updated book in 2005, the same schematic appears. But this actually really does set out for us what happens during a VO2 max test. So what you have fundamentally here is we have exercise time, and then we have our resistance here. So in order to get somebody to VO2 max, we have to progressively increase the resistance until they reach that point of volitional exhaustion. That is the point where you're at maximal cardiac output and maximal AVO2 difference. And what we can see here is that they're using, in this example, 5-minute workloads. We'll discuss workloads, durations and increments in a bit. But here they're doing stage durations of 5 minutes and increment increases of, in this case on a cycloergometer, of 50 watts. And what we can see on the panel on the right, which represents the average VO2 across the 5 minutes, you can see this response that occurs here. And if you look at that, I'm sure you're looking at that graph going, I can see what that is. That is a linear-like relationship. And it absolutely is. This is one of the important aspects within exercise physiology, is the relationship between oxygen consumption and exercise intensity is linear. Unlike the relationship that you see here for blood lactate, which is curvilinear. But the other thing that you'll notice, and you'll see it on both plots, is when the resistance gets to 250 and then 300 watts, notice what happens. You can see here that at 250 watts, this is 250 watts here, this is their time to reach a steady state. They eventually kind of get to a technical steady state. At 300 watts, it takes them a lot longer, but notice that the steady state is identical. And so when we average those VO2s out, what we end up with is an average VO2 in the region of about 3.5 litres per minute. But the VO2 is no longer rising. And this is what we term the VO2 max. That is, despite the increase in exercise intensity, there is no increase in the amount of oxygen being consumed. We cannot deliver any more oxygen. We cannot extract any more oxygen per beat of the heart. We are now at the point of volitional exhaustion. Whereas down here, below the VO2 max, were exercise to be terminated for whatever reason, we're not stopping due to an exhaustion, we're stopping due to a fatigue. And so this really allows us to differentiate between perhaps a poor performance and perhaps a truer performance in a VO2 max test. And this is reinforced for us here in a more recent paper. This was published in the European Journal of Applied Physiology 2014. So this is Guido Ferretti, and what you can see here is the same principle. So we've got VO2 in litres per minute. Don't worry about this extrapolation that they've done here. What I want you to focus on is the same principle, that we've got the increase in exercise intensity, and they're going up in about 50 watt increments, so similar to what we saw from Astran and Rodell. But notice again, the important thing is, firstly, for the majority of workloads from rest from 50 watts upwards to say 300, just over 300 watts, the association is near as damn it linear. Again, these are averages across the workload durations. But the same thing applies from about 350 to 400 watts, that you can see there is pretty much a leveling out in the VO2 response, that despite the fact the exercise intensity, the external load is increasing, the physiological response has leveled out. We get this, what is called a plateau-like response. That is, that the VO2 cannot rise any further. And this it equates to around about just over 4 litres per minute. And so that is classically what we are looking for in terms of VO2 max response. We're looking for this plateau in VO2 despite the continually rising increase in the external power or the external load. And we see the same thing here. Perhaps you're thinking, well, maybe it's just a function of the ergometer that is being used. So we go back to a paper. This is Howley, Bassett and Welch in 95. So here we've got treadmill data. So what they've got here is they're holding them at a constant speed. So this is at 7 miles per hour. So it's an American paper, so it's in imperial units. Here we've got the oxygen consumption, again in litres per minute. But notice they're increasing the resistance here by increasing the gradient of the treadmill. So they're fundamentally making the treadmill gradient steeper. But the same thing applies, that we've got a linear-like relationship across all workloads and oxygen consumption. So you can see that for a 2.5% increase in resistance, we're getting in the region of around about a half litre increase, just under a half litre increase in VO2 in this individual for every 2.5% increase in the external resistance. But the same thing also seems to be indicated here, as we saw in the previous data sets, and in fact as Hill alluded to in his data set back in the 20s, which is that there comes a point where the resistance is increasing. In this case it's the gradient, but the oxygen uptake no longer increases. We've hit, one would ascertain, or one would suggest, we've hit maximal cardiac output, we've hit maximal AVO2 difference, therefore VO2 cannot rise. This is what we call a plateau. This gives us the VO2 max, which in this case is actually about 3.5 litres per minute. So this plateau seems to be a common feature that we see, we're certainly seen across these early studies that we've shown here. And in fact, if we come to a paper that I published back in 2017 on a form of VO2max testing, we kind of set this out for us physiologically. So I'm just going to highlight the information that is important. And we wrote this: the traditionally accepted primary criterion for determination of VO2max is the levelling out in VO2 prior to the point of volitional exhaustion, in spite of a continued increase in exercise intensity, the VO2 plateau that we've been looking at. The physiological rationale for the manifestation of the VO2 plateau is that as exercise intensity increases, an imbalance ensues between the delivery of oxygen to the muscle as expressed by the cardiac output, that is Q, and the ability to extract oxygen at the muscle as represented by the arteriovenous oxygen difference, that's the AVO2 diff. So fundamentally, the ability to produce a plateau is linked to the levelling out in cardiac output and AVO2 difference. And if we start to think about what the plateau may represent, it may start to become clear. If we're at the point where cardiac output can't rise anymore, that means we're fundamentally at max heart rate, max stroke volume, and we can't extract any more oxygen per beat of the heart. If we just very briefly flick back to this image here, if we're saying that is the case, that we're at the maximum point here in terms of cardiac output and heart rate and stroke volume and AVO2 difference, we're clearly not changing oxygen concentration in the circulation, we're clearly not changing plasma volume in the course of a test. If they're all maximal, where is the energy coming from? Because the gradient has gone up in the case of this data set. The resistance on the cycloergometer has gone up in the case of this data set. Yet both show us a plateau-like response. If we go back even further, on this data set, it shows us a plateau-like response. So clearly the participant is still exercising despite the fact that we have reached the point of maximal cardiac output, maximal AVO2 difference. So where's the energy coming from? Well, as you're about to see further into this presentation, the idea or the theory that we have is that the energy at this point is actually down to anaerobic substrate metabolism. In other words, you can't work any harder aerobically because you can't deliver any more oxygen. You can't extract any more oxygen. So the only way that this occurs, this plateau response occurs, is because we are relying on anaerobic substrate metabolism. We're tapping into the finite anaerobic capacity.